Okay, we are doing a quick recording here, going through number 29, 30, 31, and 32 on the Coulomb's law assignment, the last four questions, which are quite tricky. So let's begin with 29. So here we have a ball on a string in a field. So let's draw this little ball on a string like this, okay? And the field has an intensity of 300 newtons per coulomb, and it says it's downward. So what I'll do is take another color here. Let's see where my colors are. Let's do red. Actually, let's do a crayon or something. 1 second. I thought I could do a crayon. Maybe I can't. So our field is sort of going down like this. There's our field. Okay, so that field is E, and according to the question, it's 300 newtons per coulomb. And that field, of course, is going to apply a force to our little particle that's on the end of this string. So what we have to do is we have to decide how that is going to affect the particle on the bottom on the string. Okay, so let's begin with sort of the net forces on this ball. So let me change to red. There's obviously a tension force going up. That's our tension. And then there's a force down, right? Which is the force of gravity on the ball. We know that gravity is important because they told us the mass. So that's how we know to include gravity. But there's also a force caused by the electric field. And that's kind of the hard part of the question because we don't know the charge on the ball, whether it's positive or negative. All we know is that it's 8 microcoulombs. So let's imagine what would happen. If the charge was positive on the little ball, there would be a downward, let's put it over here. There would be, remember that a positive charge would follow the field, right? So there would be a downward force on the ball if that charge on it is positive. But if the charge is negative, I'll do it over here. Remember, negative charges go against the field. So this Fe is going to be an upward force. So a negative charge will make an upward force, which should be a positive for our numbers, right? Up is positive. And a positive charge will make a downward negative. See how they're kind of backwards? With electricity, you always have to infer the directions based on the rules of attraction and repulsion and the way that fields work. So remember, positive charges follow fields and negative charges go against fields. The forces push them against it. Okay? So let's do the first case where we use a positive charge. So there would be an additional downward force here called Fe. Because the following the field, right? Following the field down. So there's my force picture. So now I can, let me see if I can just move this a little bit like that. And I can write a net force picture underneath here. And that would be F net equals the electric force plus the gravity force plus the tension. Okay? And then the net force is going to be 0 because there's no acceleration. The question says the ball is hanging on this thread, not moving, not accelerating. Now, do you remember what Fe is? Fe, it's either KQ1, Q2 over R squared, but if we know the field, it's also QE. Remember the shortcut version. And then this would be mg for gravity and our tension. Okay, so now, looking at the picture right there, you can see that the gravity and the Fe are both downward forces. So when I put in their numbers, I'm going to put them in as negative numbers, right? So Q is 8 microcoulombs. E was told to us as, I think it was 300. But this is a downward force, so I didn't leave much room. I'm going to have to move this over. Because it's a downward force, I have to put a negative number here, negative in front of it. Same with gravity, it's downward, so negative. Be careful, 0.6 grams is actually very small. It's 0.00006, I think it is, right? Because 6 grams, nope, one too many zeros, rats, sorry. 3 zeros and a 6, I think, should do it. Yeah. Okay. 0.6 grams. Okay. Times 9.8. And then plus t. So then, when we do our math here, okay, let's go back. I'm still remembering how this thing works. Okay, so 0 equals, this number is going to be, I think, negative 0.0024. And this number is going to be negative 0.00588. I'll just check my my math here. I think that looks right. And then when we add those together, we get 0 equals 8.3 times 10 to the negative 3 newtons, right? Plus t, and those are negatives. And you move them to the other side, 8.3 times 10 to the negative 3 newtons equals tension. And that's the answer that they have, 8.3 times 10 to the negative 3 newtons. Now, if we change the charge on the ball to a negative charge, it only changes one thing. We said that if the charge is negative, then this is what the field does. It pushes up. So for a negative charge, this Fe that's green here will no longer be down. It will actually be up. There's my Fe. Up. So all that does is change the sign for the number, for QE. So what all I have to do now is change this right here to a positive, which changes that to a positive. And so if that's the case, what I'll do is I'll jump down. I'll jump down to here and use a positive number. Well, now you're going to have 0.0024 minus, so that's going to come out to 3.5 times 10 to the negative 3 newtons equals t when you put it all together. And that is the second answer. So that's what you have to think about when you're doing this question. You have to think about the free body diagram and how the field creates the electric force that is now just added in along with our gravities and tensions that we did before. So that's 29. Okay, we will now move on to question 30. We'll go back to my black color here. Question 30. All right, so for question 30, what we have now is a ball. Oh, marker. A ball. And it's sort of hanging out like this on a 20-degree angle. And what they're telling us, you have to look at the little picture on the right-hand side. Now, they've drawn their field sort of beside it, but what I'm going to do is draw it right across what we did before. So what the field is doing is it's pushing this way. This is the electric field that this ball is hanging in, right? So this is the E, and this time it's 700 newtons per Coulomb. So if you think about it, what's this electric field doing? Well, it must be pushing on the charged ball that's hanging. And it's funny because the field is going to the right, but the ball is sticking out to the left. That tells us something critical. What kind of charge goes against the field? A charge that's negative would push this way, wouldn't it? So we know that the charge on this object must be a negative charge. in order for this ball to be pushed against the field. And that's going to be important later, as that's one of the answers to the question is, what is the sign of the charge on the ball? So if we know that it's a negative charge because it's going against the field, pushing the ball outward to the left. If it was a positive charge, the ball would be way over here on this side and it would be pushed this way out to the right. But it's not. So we don't have to worry about that. So what I'm going to do now is I'm going to draw a free body diagram with all my forces underneath here, down a little bit. So what I have is I have a ball. There's a tension pulling up this way on the string. And there's also an angle that goes with that tension of 20 degrees. There's a gravity force pulling down, which I'll draw in red. And if you go back up to my picture, we said that there's a electric force caused by the field pushing straight out sideways. So let me draw that in green. That's what's causing the ball to hang at that weird angle. So here's my situation. Here's my free body diagram. Well, what I'm going to have to do is resolve my tension forces because they're not straight up and down or lefty-righty. So this is my t cos 20. And this is my t sine 20. T cos 20 is about 0.94 t. So we can use that. And sine 20 is about 0.34 t. Okay. Now, F net, x's and y's, just like before. So you see what's happening. We're doing this the same way we would have done a problem like this in our mechanics unit, but we're adding in electrical forces that are caused by fields. So the only real trick is for you to figure out the part up above here and figure out which way the electric force is actually pushing. And you have to look at the field and determine whether the charge is negative or positive and which way it's going against the field or with the field. Okay, just like we did there. All right. So now let's do the math. So F net, let's see, F net x is Fe, all the sideways arrows, and t sine 20, or Tx. Let's call it Tx. Okay, now we know this ball is just suspended here, so we know that the net force is 0. How do we do the Fe again? QE, right? Just like mg, remember, for gravity. So QE, and the x is 0.34 t. Now, let's put in our numbers and let's look at directions. Notice how the QE, the green arrow up above, right, way up here, is to the left. So it has to be a minus. So we get 0 equals minus. Now you notice that this minus is not about, doesn't mean the charge is minus. This minus I found out by looking at my picture after I determined which way this thing was going. Now it just so happens that my charge is also minus, but I had to figure out the direction from the question, right? There was no obvious way to just assign it a minus number until I used what I know about electric fields and which way charges go. So again, you have to infer the direction from the context and then translate that into a plus or a minus for left or right. And that's what I've done here. So then I have negative Q times 700. I don't know the Q, but I know the 700 and the 0.34 T. Well, I'm at a standstill because I have a T and a Q. I can't finish this. So guess what I'll do? I'll just leave that. I'll leave it right there where it is and come back to it later, and I'll try the F net Y and see if that gives me anything useful. That would be, going back to our picture, the up and down arrows of Fg and the T cos 20. So let's go and put that down here. Fg plus Ty. Again, it's a 0. This will be mg, and this will be the T cos 20, or the 0.94 T. Now that was an up force, but the gravity is a down force. So when I put in my numbers, once again, have to be careful, negative, the mass 0.00006.6 grams multiplied by 9.8 plus 0.94 t. So t will come out to, when I do all that math, 6.3 times 10 to the negative 3. That's the tension. That'd be newtons, right? So now I can use that number back up here. I can take that number and substitute it right up here where the t is. So that means if I do that, I go back to my F net x equation, right? And it would read 0 equals negative q times 700, and then plus 0.34, but in place of t, I can now insert this number. That's a 3. I do my math, I multiply a little bit and divide and work everything out, and what I should get is a q here that works out to 3 times 10 to the negative 6. And that would be coulombs. Don't forget your units. And that is the answer. 3.1 is what they have there, but 3 times 10 to the negative 6 is good. Now, what's interesting is this came out to a positive number. And that's because we were just determining the magnitude of this force. What we have to do is go back to figure out its direction. We already did it, but we have to go back and see why this answer is coming out positive right here. Okay? Because that's the magnitude of Q. But when we go back here, we determined that in order for this to work, the electric force had to be to the left. It had to be this guy to the left. And the only way to get a force going to the left in a field that goes to the right is if your Q is a negative charge. So the answer, even though my numbers came out to positive 3 times 10 to the negative 6, in this case, looking at my context, it's a negative 3 times 10 to the negative 6 Coulomb charge. And that's why it says negative 3.1 for the answer. See, directions are tricky with electricity. Okay, now we'll go on to number 31. So we'll just draw a line there and carry on. Number 31. This one is a little bit different. So what we have here is we have an electron. Okay, so let me just draw this little electron here. And it's being shot out along the x-axis. So we'll draw it like this. And it's got a v. So it's got an initial v of 3 times 10 to the 6 meters per second. It goes 45 centimeters, 0.45 meters. And then it stops. So this is actually a V1 then, and the other one is a V2 of 0. Whenever you see two V's, that tells you, that means something is decelerating, slowing down in this case. An acceleration like this means there must be a force. What force could there be? Well, it says it's doing this in a uniform electric field. So let's draw the field. What kind of field would make an electron slow down? If we go back to that other question, remember electrons go against the field. When the electrons accelerate, they speed up against the field because they're negative charge. So in this case, if an electron is slowing down, the field must be going in the same direction. So our field is across like this, that this is happening in, this way. That's our electric field. E. Oh, I meant for that to be yellow. Let me erase that so we're color-coded, and let's make that yellow. They don't tell us anything about E. That's what we're looking for. But you see how I figured out how it was going? Do you see how I figured out its direction? In order to make an electron slow down, it has to be in the same direction because electrons want to speed up against the field. So an electron in this field would speed up to the left and slow down to the right. So it's weird. It's backwards to what you would think because the electron is negatively charged. Okay, now that we figured that out, we can just look at the net force on the electron. Okay, now, if it's slowing down and we have the V1 and the V2 and the D, you know what we can do? We can figure out the A before we do the net force. If we do the net force first, we're going to see we need the A. So if you did that first, it wouldn't matter. It would just mean that you had to leave it for a minute and get the A and come back to it. But we know we can kind of, this smells like an A, doesn't it? So let's just get the A using a black here. Let's go up a little bit and we have V2 squared. What's this marker? Okay, I'll get it right yet. V2 squared equals V1 squared plus 2AD. 0 equals 3 times 10 to the 6 squared plus 2 times A, and the D is 0.45. And when we do this, crunch this out, you'll get an A of negative, which is what you want because it's slowing down, right? 1 times 10 to the 13. Very large A. Okay? Now you might say, isn't that faster than the speed of light? A is not a speed. A is how fast speed can change. So there's no limitation on how high that can be. Okay? A V can't be faster than light, but an A can. Okay, so there's our A. So now let's go and do the net force on this electron. Well, if you look at the picture, the electric field is causing a force. And as we said, that force would be going against the field. So there's a force sort of this way on the electron. That's the force, right? Okay, so it's a lefty facing force. Remember that. Let's now go down and crunch out what that would be. Net force. F net. Well, what is that? It's an electric force. It's the force of the electric field. So that means F net is MA and this is QE again. That's all there is. We don't have to worry about gravity here. The question doesn't really want us to worry too much about the force of gravity. It's kind of, you don't really know that. I know that because I've worked out the answer and it doesn't include gravity. So there's just a slight thing you have to just trust me on that. Okay, so don't worry about gravity in this one. And you might say, well, how can we worry about gravity in the last one, right? They're almost the same. Well, a tiny ball, 0.6 grams, that's significant. But remember the mass of an electron, 9.1 times 10 to the negative 31. The gravity on an electron is pretty much not even worth looking at. So we don't have to add over here plus, we don't have to add plus Fg because it's too small to worry about. Okay, so now we just finish this off with our numbers. So 9.31, or no, what is it? 9.1 times 10 to the negative 31 is the mass of the electron. We had an A up above, which was negative 1 times 10 to the 13. And now, QE. The charge, since this is an electron, is 1.6 times 10 to the negative 19, right? And then E is what we're solving for. Now, I want to show you something. Look at our picture. I'm going to have to make some space here again. Me and my jumping ahead. Look at our picture up here. We said that that force had to be a lefty-facing force in order to slow this electron down, right? Which means it must be a negative value. So when I put it into my equation, I best put equals a negative number there on this QE to show that it's a lefty force. And so then what happens is when you multiply all this out and you divide and you solve for the E, you get about 57, and that would be newtons per Coulomb, and that is your field strength. And the positive number comes out because, look at the way we drew our yellow lines, positive. So it's a little bit tricky with directions. I understand that. But you do get the hang of it the more you go through. Okay, the last question, 32. This one looks hard, but not so hard once you realize what it is. So this is like the level 5 question, right, on this particular test. First of all, let's draw a picture. This is 32. What do we have? A particle has a mass and a charge. Okay, so let's draw this particle. Its charge is negative E, so we'll just draw it like this. So the Q for this is negative E. In other words, it's like an electron, and its mass is just going to be M. All right? We don't have a number, but they're just telling us the mass is M. And what's happening is it's being shot into a field. It's being shot to the right. So initially, it's being shot this way. But let's draw the field. The field is downward. Electric field facing down. So let's draw that. There's my field. Okay. Once this electron goes into the field is going to push it. Or I'm calling it an electron, but it might not be. But this particle, right? It has the charge of an electron. So look at the charge. It's negative, which means if it's going to get pushed, it'll be pushed against the field. So what will happen is as soon as this goes in here, there will be electric force pushing it sort of up this way. That's electric force, right? Fe, pushing it up, which means its path will begin to get pushed up and it'll curve up like this. So initially it was straight across, but as soon as it hits the field, the pushing up makes it curve or accelerate. So look what we have here. We have a particle that sideways motion is constant speed because there's no sideways force, but its vertical uppy-downy motion has an acceleration. It's being forced and changed its direction, which changes its acceleration. This is exactly like another thing we learned in grade 11. It's the upside down version of shooting a ball this way and letting gravity pull it down. Here we have the gravity force pulling down and constant speed sideways. And up above, we have the electric force pushing up and constant speed sideways. So really, this is a projectile, but it's an upside down projectile because with electricity, we can make things go up or down. But we're going to treat this just like a projectile. So let's think about our accelerations first. That's what part A says, the accelerations. Well, look at how projectiles work. With our old fashioned projectile, we had constant speed on the x, or sideways, and we had acceleration due to gravity on the up and down. So, just like that, we now have constant speed sideways. So the acceleration sideways, or what the paper is calling ax, it's 0. There's no forces sideways. But the ay is a little bit different. So how do we get that? Well, how would we do the ay? Well, we'd have to look at the uppy-downy forces. So the net force, I'm doing the y now, F net y equals Fe. That's the only force, right? QE. All right. So in other words, Fe is replacing gravity in our picture. So Ma for the F net y. And how do you do electric force? QE. Remember? Now look at this equation. Just solve for A, and you get QE over M. But remember what the charge was? Remember? The charge, Q, was E. It's a negative E, so it's an E for its magnitude, right? And so if you just replace that with a little e, you get A equals a big E times a little e, just flip them around, over M. That's the AY. And that's how they got their answer for the second part of that. AY equals electric field times charge over mass. All right. Now part B says, what are the horizontal and vertical components of the acceleration? I'm sorry. No, part B says, what are the horizontal and vertical displacements, F, X, and Y? All right, let's go up here. Let's do our good old thing. What do we always do? Vertical and horizontal, right? For a projectile. And for here, we have a D, we have an A, a V1, and a T. And over here, for horizontal, it's a D, a V, and a T. We're going to call the vertical distance Y and the horizontal distance X. That's what they did to get their X and Y, right? And what's the horizontal speed? Well, it's whatever the V was. It says in the question that it was projected with the horizontal speed V. So it's just a V. And then the T, of course, is just the T. And so if we do this very easily, D equals VT, we've got X equals VT. That's how they got their part B answer, X equals VT. Now, let's go over here to the Y. V1, what was the vertical V1? It was a 0, wasn't it? Because the speed was directed horizontally. And T, what was A? Well, we found A. It's this guy up here, EE over M. So we'll put that in here for our A. And then what do? Well, we do our equation for that, which is, let me just do it down here. D equals V1T plus a half AT squared, right? These are the equations, the D equals VT, and this one, these are the equations of the horizontal and vertical projectiles. And because this looked just like a projectile, we're doing projectile math. So D is X, V1 is a 0, so that disappears. Then we have 1/2 of EE over M times T squared. And that is exactly what they have. 1/2 EE over M times T squared. So that's where they got that from. Okay, now, if you're still following me on this, what do we normally do when we were trying to solve projectiles? What we normally did was we took these two equations that we had here, this one and this one, and we put in numbers, and usually there was a couple numbers missing. So what we had to do is we had to use one and sub it into the other. Remember? We had to take one out, work one out as much as we could. And what we usually did is we isolated this one for T. T equals X over V. We usually solved this for T, and then we substituted that into the other equation where the T's were, one there and one there. So what would happen if we did that, right? If we were trying to solve this question. Let's move up a little bit and let's make that. We've isolated this side for T, and we're going to put it in there. I'll just keep going in red. So we would have, let's see, this, I made a mistake. I just realized it. I mean, some of you probably are noticing I got an X here. That was the vertical, right? That X should have been a Y right here. This is a Y. We already did the X up here. This should have been Y, my mistake. And that's what it is in the question too, right? Y equals 1/2 EE over M times T squared. Okay, so we're going to substitute this into that equation. So we get Y equals, now the V1T was a 0, right? So there's no point substituting it into there. That's going to be a 0 anyway. So I just have to worry about this part. So that's 1/2 A, which is EE over M, multiplied by X over V squared. Right? And if we just kind of shove this around a little bit, we can get the answer they have. That's 1/2 of EE over M multiplied by x squared over v squared. So we just move the little, multiply the v squared into those brackets, but leave the x outside to get the form that they want, right? We get y equals 1/2 EE over m, and the v squared goes with it, times x squared over here. And that's what they have. But this can be further simplified into, if you were, I don't know why they chose that particular way of writing it, but if you were fully simplifying it, you'd multiply the half in, right? And you'd multiply the x squared in, and you would basically get E x squared over 2mv squared, like that. And that would be your answer. But this is the answer that they have in the book. So what did we do there, just to recap? We used our two vertical and horizontal equations, just like we did for normal projectiles. We took the horizontal, isolated for t. I'm going to change my color so you can see what I'm talking about right here. And then substituted it in there like we would have done if we were solving a question, and just worked it out without the numbers and got to the end. So that's how you take care of the last 4 questions on the assignment. If there's any other questions, I know I did tell you to have this handed in by Monday, but of course, if you need to ask me a question or two on Monday, you can certainly do that during class, and you can hand it in after that, okay? No worries. All right, end of assignment.